it diffract, because all the plane you would expose, you will see all the plane because of all the orientation of your powder in your sample. Okay, and every chemistry department, I'm sure, has powder diffractometer. It's an extremely powerful tool for material science. If you are making powder, right, you just have to put your powder inside, and you get all the orientation, and from there you can determine the structure of the parts. Okay, so very simple thing, and the basic and the physics behind this is also very simple. That, as we know, is based on Bragg's law. Bragg's law is very simple. Bragg's law just say that the path length difference must equal to an integer times the wavelength of your light that give you diffraction. And the path length difference is depending on this interlayer spacing d here times this theta, which is the incident angle from the plane. So the theta is the angle measured from the surfacing. So if I look at my surface here, light coming in, the theta is in this direction. This is my theta right here. And I can figure out the first, I have a wave, right, come in, scatter off. So usually I write a wave as a plane wave, so it's kind of like this. You imagine a wave front coming in like this, right? And wave front, plane wave is usually written as e to the I k dot r. This is how mathematically people expand. The way to see this is that you can expand this exponential into sine and cosine, right? E to the I k dot r, just cosine k dot r plus I sine k dot r, right? That's the expression. So it's kind of a plane wave. So usually you write like this. Physicists write it like this. And then you scatter off this point, right? So another wave coming out, right? This wave coming out like this. Another wave coming out like this. And this is so-called elastic scattering. In other words, the energy of your wave does not change. You do not lose energy. It's still the same. But the direction of your wavefront has changed. So here you have e to the I k pi dot r. This k and r are both vector quantity. So that's the scattering off one point. And now, if you imagine you're scattering off a second plane below the first plane, and you have same thing. You have wave coming in and wave coming out in parallel, and you consider the distance, the path that travel, the difference between the path traveled by these two beams. And the difference is this bit here, right? So you can do geometry, because here is the same, here is the same. So the only path length difference is just this, okay? So the path length difference here will be just like this, and then you can work out the geometry, right? Because this angle here is equal to this angle, right? And this d spacing is the interlayer spacing. So this angle, so this distance here is just sine theta times this d spacing, which is this angle. And you multiply by 2 because you have twice this path. So that's how you get this 2d sine theta. So it's very easy to derive just by simple geometry. And in order to have diffraction phenomena, in order to see a line or spot in your diffraction pattern, this path length difference has to be an integer times the wavelength itself. If you don't have that, you would have destruction interference, and the wavefront would cancel each other. So you would not see anything. So that's Bragg's law. I think we're familiar with this. And here where the magnitude, I just say where the magnitude incident and outgoing wave vector are equal, because at least energy-wise, because we have elastic scattering. We don't consider inelastic scattering at this point. And when we're talking about energy, kinetic energy, of course, K here is just is similar to my momentum. K is a wave vector, is a momentum, if you like, is just Planck's constant times this vector. You can think of it that way. Or you can think of this k vector as reciprocal space, reciprocal length. So here, because this component has to have no units, so if you have k dot r, so k is reciprocal vectors like this. Sometimes called the wave vector, because that's the propagation direction of the vectors that you have. So what you got then is that usually when you say elastic scale, you mean the square, because k is proportional to momentum. You can think of it that way. And then you have k must be equal to k pi equal to 2 pi divided by lambda in order to satisfy this condition. But you realize, of course, there's k is a vector, so even though the magnitude, the square of this vector, the incoming wave is equal to outgoing wave vector, the square of those two k pi must be the same, but the direction has to change. Okay, so in other words, k pi must equal to k plus some change in direction called the momentum transfer vector, because you add a third vector to here in order to change the direction of k to k pi. Okay, and that third vector is called the momentum transfer vector. Okay. And this is the interesting part, because the momentum transfer vector will introduce something called residual lattice vector, as we'll see shortly. Okay, so what we have then is that we have this residual lattice vector. We're going to talk about residual lattice vector. What is residual lattice vectors? We sort of get leading into it from this thing here, because this in some way is like a residual space. K is like residual space because it depends on 1 over lambda, isn't it? So it's proportional to the inverse space is 1 over lambda. So that's why it's sort of momentum transfer vector or momentum vectors is like reciprocal space vector. And here we're talking about lattice based on this residual space vectors. So let's look at it closely, a little bit closely, because this is a kind of fundamental concept. And it's a little bit tricky concept that you cannot think in terms of inverse space or reciprocal space. Okay, by definition, what you think about is that a crystal, when we talk about crystal, it has 3D symmetry. And what does that mean really? It means that it's invariant under translation operation. So if you move, let's say you have one point, you identify one point, and you translate it, just linear motion of that point by this amount, by this translation vector, some constant times A, some constant times B, some constant times C. A, B, and C are the lattice vector of your crystal. In other words, if I move myself from one point to another by this T vector, translation vector, I would not know that I have moved, because I stay with one atom in this lattice, and then I move n amount of A spacing and these different integral of this A, B, and C distance, I would not notice any change. And that's what we meant by symmetry, right? Because you generate these periodic properties of your crystal in 3 dimensions. So by definition, a crystal is invariant under translation of this form, this translation vector T. Any physical property of a crystal is invariant. In other words, you will not change if I just add a T to my position. So you think about electron density, for example. So let's pick this property as electron density, and I write electron density as n as a function of r. R is some position in my lattice. Then, according to this, if I shift my r by t, t is the translation vector, that electron density should be identical to the original point before shifting to another point by this t vector. And that's what it means mathematically, translation symmetry. right? Should be invariant under translation operation. So that is the key point about crystal. This is define everything, all the property you see, right? This translation should be invariant under